In our next example, we're going to be looking at events a slightly different way than we did in the previous video. So, first example, find the probability of drawing the given cards from a standard deck of 52 cards, A with replacement and B without replacement. So when it says drawing the given cards, a spade and then a club, I could think of this as having the word and, a spade and a club. That's what I'm going to draw. Now, if I'm drawing them one at a time and I'm replacing the cards, that's what I'm going to work with first. So, option A. What's the probability of drawing a spade and then a club if I'm replacing the cards? Well, first of all, what's the probability of drawing a spade? Well, that would be, 13 spades out of 52 possible. I can simplify that to 1 out of 4. That might be my probability of drawing a spade. Now, if I replace that card, I put it back in the deck, and then I draw a second card, and I want to get a club next, my probability to find a club is still 13 out of 52. I put the card back, the original card, it's still in there. So there's 52 cards left again, and I have 13 clubs in the deck, so 13 out of 52 is the same as 1 out of 4. Now, I have both these things occurring, the word and is present, so I need to multiply those two probabilities together. So the probability of getting the two cards that I want, in this case, would be 1 out of 16. I'm going to keep that same principle going over here with a different situation. Again, with replacement. See how this works. So, with replacement, I'm going to first try to draw a jack. Okay, well there's 4 jacks out of 52 cards. 4 out of 52 would reduce to 1/13. Now, if I replace the card, I put it back, it's still there, it's still an option. So if I wanted to draw a second jack, remember the first one is back in the deck, it's still there, it's still available. So I have, once again, 4 jacks out of a possible 52 cards that I might draw. So, taking 4 out of 52 and reducing it, again, is 1/13. Now, these being independent events, I multiply the two of them together. 1/13 times 1/13 is going to be 1 out of 169. Here's my probability of drawing 2 jacks. If I draw a jack, put it back, and try to draw another jack. Now, I want you to notice what happens differently when I work with the second option, which is without replacement. So first of all, the spade and club situation. If I'm going to draw a spade first, well, that probability is still going to be 1 out of 4 because there's still 13 spades out of 52 possible cards. Now, the club, the without replacement part is the key here. So now, if I have successfully drawn a spade, that means I have the spade that I want. The number of clubs in the deck would still be 13. All 13 clubs are still there. The difference is in the total number of cards available to me. If I don't replace the spade that I drew first, I now have only 51 cards remaining in the deck from which to draw. Multiplying these two items together, I end up with a nice 13 out of 204. Slightly different scenario than it was if I replaced the card in the deck. Now let's see how that affects our jack problem over here. Well, first of all, to draw a jack, there's 4 out of 52, so that means I can reduce that to 1 out of 13 right away. Now for the second option, I'm going to multiply, then another jack. Well, now let's think about how this affects it. I drew a jack. So now, not only have I affected the total number of cards, if I'm not replacing it, there's only 51 cards available to me, but I've also affected the number of jacks that are in the deck. So since I took one of the jacks out, now instead of there being 4 in the deck, there's only 3. So I have 3 jacks out of a possible 51 cards still in the deck. And when I multiply these two fractions together, I end up with a fraction that can be reduced. Sorry, I'm doing this quick because I have it written down. 1 out of 221 is now the probability of drawing 2 jacks if I'm not replacing cards in the deck. So you'll notice that our probability is different based on if we're replacing or we're not replacing. So when I replace the card in the deck, my events are still independent of each other. They don't, what I drew the first time doesn't affect the second time because I put the card back. It's right back to the same probability no matter what. But when I keep that card out, now I have affected the probability of the second event happening. So now the second event depends on the first event. And if I'm looking at the probability of dependent events, I have to change my thinking just a little bit. I'm still multiplying, but what I multiply by is slightly different. So here's our description of dependent events. Two events, A and B, are dependent events if the occurrence of one affects the occurrence of the other. The probability that B will occur given that A has occurred is called the conditional probability of B given A, and is written as the probability of B given A. So that vertical bar means given. Definition: if A and B are dependent events, and the probability that both A and B occur is the probability of A and B occurring, the probability of A times the probability of B given that A has already occurred. So when I was looking at the cards, the probability of pulling a jack, okay, well there's the probability of pulling a jack regular, times the probability of pulling a jack given that I have already taken one out. Okay, so I'm still multiplying, but I have to adjust the second portion of the probability. The example I've got for you here is this. The table shows the results of a fake survey that I took of Shoreland students. Fake because I didn't actually take this, I'm just assuming some things here. What is the probability selected that a randomly selected student is female, and if female is a Bears fan? So first of all, let's figure out what's the probability if we randomly select a student that we get a female. Well, I've got 100 male Packer fans, 40 male Bears fans, 80 female Packer fans, and 35 female Bears fans. So I'm just going to add up a couple things here. First of all, I've got, let's see, 140 males and 115 females, which means I've got a total of 255 students that were in my fake survey. So, first of all, what's the probability that a randomly selected student is female? Well, to do that, I'm going to look for the number of females, which I said was, adding these two together, 115, out of the possible number of students. Well, there were 255 students total in my survey, so the probability of selecting a female student would be 115 out of 255. Now, I could reduce that to 23 out of 51, and if I wanted to have that as a decimal, that's approximately 0.45, so it's around 45%. So that's not so bad, just one event happening. But now, I have a conditional probability. If female, what's the probability that this student is a Bears fan? So when I do this, the probability of A and B happening here. Probability that the student is female and a Bears fan. So the probability that the student is female, first of all, I already knew it here, so that's the probability of A. I take the 23 out of 51 that I had from the previous problem, but I'm going to now multiply it by the probability of B given A. The probability that my student that I'm talking to is a Bears fan, given that they are female. So for that purpose, I can take, let's see, the probability that the student is a Bears fan and female. Let's see, there's 35 female Bears fans, so 35 out of how many? Well, it's not the total 255, it's the fact that they're female. I already have limited to the fact that they're female, so there being 115 females, I have 115 for the denominator of that fractional probability. Now, multiplying those two big numbers together, I get 805 over 5,865, which is kind of a big, goofy looking number. If I were to reduce that, it actually reduces down to 7 out of 51, which is convenient, and is approximately about 0.14 or 14%. So that's the probability of selecting a Bears fan, given that I've selected a female from the survey that I have taken.